So another form of recap, and I add in a little stuff on the surface contact already. Alright, so we talk about the Hertzian stresses and things like that. Alright, so how to calculate acceptable surface thickness and Brinell hardness calculation. So we now need to talk about the Brinell hardness testing now. So let's take a look at that. So so far we have cleared away all this already from the previous 5 videos. So now this one. Yeah, let's go. A common hardness testing is a Brinell test method, alright, in terms of all this, alright, and the strength unit is kg per millimeter square, or per millimeter, okay. So under conditions of cyclic loading, blah 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 blah. So all in all, alright, is is being used. The equation for calculating BHN, the Brinell testing, right, is the applied force divided by all the diameter, or the diameter of the ball. Okay, so yeah, I think you get what I mean already. So you just, and also the diameter of the indentation, the impression diameter, I think. Yeah, so the impression diameter. So so after looking at this, I think this is more legit. Alright, and this is because previously we were saying that the impression radius, we have some problems with it in the concept. So I think now the concept is quite clear now where the hell is the impression radius. Because when you talk about impression radius, you're talking about this particular point where it's being impressed. So this impressed radius is talking about this radius over here, imaginary radius, in case that you forgot or whatever. So as you can see, this indentation radius is different from the bigger radius. Alright, so yeah, take note of that. So once you get this, you can calculate for your BHN already. Alright, it's just a simple equation, and I don't think you need to memorize that. Yeah. So next we talk about the Plasticity Index, alright, where it actually determines the stress level at a point of contact, or between the two surfaces, alright, and as to cause elastic deformations. Alright, so in this, so let's take a look in a more detailed way. So if you were to come here, that would be better. So when you cause elastic deformations, so okay, so if the index is less than 1, alright, if index less than 1, elastic deformation occur. Alright, if it's greater than 3, alright, plastic deformation occur. Alright, elastic deformations is elastic, so it means that it will come. So this is strain, this is stress. Elastic is in the elastic region. It will not deform, or it's just elastic, and then it comes back to its original length. Alright, but if the index is higher, alright, then you start to plastic deform, which is permanent deformations. Alright, so take note of that, very important. So index equals to 1, elastic. Alright, more than 3, alright, then permanent deformations. Alright, so this is the equation to determine your plasticity index. Alright, and I don't know whether you need to memorize. I don't see that he asks us to memorize that, so you need to also take note of it in case that you want to calculate, you know how to use it. So this is the stress over here is the root mean square of the asperity peak height. And this is the surface of your material, alright, a bit rough. And then I am looking forward to how to determine the actual surface, alright, of mine, because you see my surface over here is a bit rugged, alright, so I don't know how to determine the actual surface, alright, because for example, this is my material, alright, this is my material, okay, and then over here I can say that this is my thickness. I can also say that this is my thickness, since maximum is over here. Or nonetheless, I can also take the average of this thing, alright, which is somewhere over here, then I say that this is the overall thickness. Alright, so therefore this is the meaning of the root mean square. Alright, so the root mean square is somewhere lying in between. Alright, so it's trying to go in over here to see where's the best line ever. Alright, so you can go to access page 11, alright, or you can go to the video 9.3 topography, alright, but the explanation over there is not good, alright, but I think still can help a bit alright, so be mentally prepared that so far my explanation sucks within these few videos. I don't know why, I think I suck anyway. So after you know your hardness of the material, hardness of the softer component, so it's the hardness of the softer component, alright, interesting. So and then you need to find your Young modulus, equivalent Young modulus. So as you can see, all in all, you need to memorize the equivalent Young modulus equation, which is all along here. So this equation you need to memorize. Okay, please memorize that. Okay, so all in all, you just need to apply. And mean radius of curvature of the aspirated tip surface. Alright, so over here I think I need to update again. Alright, I don't know what the hell is going on. Starts to tackle me a bit about this part. Alright, whether my explanation over here is it correct. Alright, this is the CLA, the center line thing, and then this is the RMS, root mean square average. So at first I thought that both equations are finding the same thing, but end up I may be wrong, or I may be wrong. So I'll update to these two videos later on in later parts. So I'll just keep it here first. Give me a while. The important thing is that you need to know the plasticity index, the criteria, and also how to sub in the formula. Alright, but how to derive the meaning, alright, I'll leave you to think about it in the future if you need. Alright, so yeah lor. So if you were to sub in the H is the hardness of the softer component. So you're going to talk about subbing in the amount of applied force and amount of applied force regarding the Young modulus of the material. Wow, never mind, I'll leave you to think about it. But the next one is cyclic loading. Alright, now over here nothing much I should say. Yeah, so there is three types of graph. The first one is the tension compression loading. Alright, so tension compression loading is most importantly I think is the bending loading, because over here if you were to bend, alright, I think you know what I mean already lah. So over here this is compressed, this is tensile, over here this is compressed, over here this is tensile, over here is compressed. So the tensile compressive loading is this type of loading. Okay, oh sorry, no, sorry, not this one. So I think is that if you have like a soft material, so you press and then you I don't know maybe you have this material, you press it, then after that you pull it again, you press it and then you pull it again. So this type of loading onto the material is this type of curve. Okay, so yeah, don't think about this anymore. Alright, I may be wrong, but anyway, so yeah, if it's a tension loading, then your graph is a higher amplitude. Okay, and then if you have a spectrum that is you don't know what the hell is going on, then you're talking about this type of weirdness graph. You don't know what the hell is going on, or it may be a mixture of in between them or other stuff. Alright, so you need to determine your stress maximum and stress mean, alright, in order to do certain stuff and to predict the amount of stresses that is occurring. The takeaway on these slides is that you need to determine your maximum stress properly. Besides determining your maximum stress, you also need to determine your mean stress. Alright, what is the mean stress? And then once you're having these two settled, then you will know how to evaluate a certain stress state of the material and things like that. Alright, I don't know why those which exceeds the shearing of the material will contribute to fatigue loading. Yeah, this one you need to find yourself. I don't know what the hell. I a bit checked already, I'm very hungry. And fracture aircraft engine crankshaft. So these are all the stresses that may occur. The problems lah. So I click the picture, I think I can click the picture, so give me a while. So fracture aircraft engine crankshaft. Just to show you, the crankshaft is something like that, like a piston type of thing. Alright, no go into details. Alright, but so the crankshaft itself, alright, the fracture aircraft engine crankshaft, the beach marks are the sign that a crack actually progressed. Alright, was due to blah blah blah. So the beach marks is something like that. So it's like a bear crawl. So this is the bear crawl. The bear actually crawl onto the beach, the tree. So we're actually causing the beach marks. So these are all the beach marks. So when you see this type of marks, alright, especially in this scenario on this metal piece, if I show you the metal piece thing, this is the beach marks. Okay, so these are all the beach marks. Okay, these are all the beach marks, like some like the bear claw beach, and this one over here is where the crack starts to occur. Alright, so the beach marks is the initiation of the crack. That's what I believe. The marks are a sign that a crack progress across the part. Alright, so the pitch mark is it tells you that the crack starts already, so you need to be careful. And yeah, so I think all in all, this is it for the Brinell hardness testing um, and the plasticity index and a few cyclic loading graph that you may want to also know. I think this is it lah. So yeah, see you.